Good morning, everyone. My name is Saad Oda. I am a TA for Heat Transfer Lab 5 for EMCH 362 this fall. A topic, measurement of thermal conductivity value of two different materials, metal and non-metals material. The main objectives of this lab are to measure and understanding design to acquaint student with the following. First, to study the thermal conductivity of engineering materials, how to measure it. Second, to find the thermal conductivity of brass using arm-filled linear conduction apparatus. Finally, to find the thermal conductivity of PL using a C-therm. From the second law of thermodynamics, everyone should know the second law of thermodynamics. It is not possible for heat to flow from a cold object to the hot object without work. It's never. So heat flows spontaneously from a hot to cold object when a hot and cold body are in thermal contact. They are exchange heat energy until they reach thermal equilibrium, with the hot body cooling down and the cold body warm up. This is natural phenomena we experience all the time. So it depends on the thermal conductivity. If we are using the metal, what kind of material? It depends on K thermal conductivity. This is what we are going to do in this lab. So in order to do this experiment, we are trying to use the famous Fourier law of conduction. So the goal to determine the thermal conductivity of metal using 1D heat equation. A theory behind this heat flows is given by Fourier law of heat conduction. In general, good conductors of electricity, metal like copper, aluminum, or brass, gold, and silver are also good heat conductors, whereas insulators of electricity with plastic and rubber are poor heat conductors. So it depends on the thermal conductivity. We are using this equation. Everyone knows this the equation for Fourier law of heat conduction. A Q equal minus K thermal conductivity A delta T over delta I, where thermal conductivity A area of cross-sectional through which heat flow, delta T over delta Y temperature gradient along y-axis, Q rate of heat flow, total Q the heat, Q input minus Q losses. Since we are insulated with the insulation, it means there is no heat go from this system to the out of the system. So the heat losses we are assume is zero. So this is the zero heat losses. Therefore, Q equal Q input. So at the boundary condition we are using, so at y equals 0, t equal t1, y equal L, t equal t2. So just give you a little background of how to use the heat conduction. So data acquirement to measure the thermal conductivity, we are using the arm-filled lab apparatus. This is the arm-filled apparatus with a power supply heat source. This is the power supply. We apply the power to the arm-filled lab apparatus to have a power. Heat source HT10XC. After this is the thermocouples. 8 thermocouples are used to connecting with the sample. These thermocouples connected to the is called a data acquisition. This is the data acquisition, connecting to the data acquisition. After that, from the data acquisition, connect to a LabVIEW program. From LabVIEW program, we record the data acquisition, send a signal to the lab program, and then after that you get a temperature. So as you can see from this figure, the cross-sectional of the linear conduction model, we call this is linear conduction model. There are total 8 thermocouples on those linear conduction model. And those thermocouples, they are labeled with the number 1, number 2, 3, 4, 5, 6, 7, 8. And then thermocouples connect to the, as we said, connect to the a DAC system. After that, connect to the LabVIEW, connect to the computer. Let's explain the linear conduction. Linear conduction, we called a 3-layer. So the hot layer, which is the top, this is the hot layer. A hot layer we called hot layer. There are 3 thermocouples connect to the hot layer and where a heater connect on the top. And the bottom we called a cooling layer. This is the cooling layer, where the cooling water go in and out to cool the system. Make sure the water going to the system and then out of the system. We need to make sure the water, because otherwise if you shut down the water, the system will burn out. Maybe take 1 hour and then the system will burn out. Make sure the water, which is here in this figure, this is the cooling water. The spacement position sandwich between the hot layer and cold layer, which called that we are going to measure it, thermal conductivity. Here you can see this is very clear for the distance. To find a thermal conductivity of the material we are using, it's called the brass sample. The brass sample of the diameter of the brass sample, 25 millimeter. We are going to calculate the area. Area is equal by over 4 d square. So d square, which is 25 millimeter. So the length of the brass sample, 30 milli per minute. Millimeter. This is the length. The distance between thermocouples, which is here, which is delta x dash equal 15 millimeter. So you need to calculate the hot layer and T cold. You need to find the temperature here and the temperature here. If you find the temperature, how to find the temperature T cold and T hot? By using, you can go to the YouTube by using interpolation or extrapolation. It's incorrect if you give me the 3 by T4 plus over 2 equal to, this is wrong. This is wrong. So you need to find the interpolation between how to find the T hot. It's called T hot. Here this T cold. To find the thermal conductivity, as from the linear conduction, K equal Q delta Y over A cross section delta T. So delta Y equal 30 millimeter, right? Delta T, which is T hot minus T cold, right? Once you find the T hot, find the T cold, applying this equation, you want, and also you have the area here by over 4d squared, you will find the K thermal conductivity. Very straightforward, it's not difficult, right? So that's it with this need. So let's go another slide. This is the sample data from the previous. So you need to make this table. This is very important table. You need to make this table in your report. Include this table in your report. But this is data. You don't need to use this data. This is from previous. But I'm going just to show you. So this what? How to find the power? Equal V time I. You have the voltage 13.5 and then you have the ampere which is 1.31. I will give you in the Excel file. So cross-sectional area and heat suction high temperature, which is G1, heat suction temperature middle MED temperature T2, and heat suction low temperature T3, and intermediate T section T4, intermediate T section section low temperature T5, and cold, because this is in cold and cooling section, cooling layer, cooled section temperature T7, and then this is the T8. So, and then you will find the T hot as I explained in the previous slide, and also you will find the T cold, right? Once you find these temperature, how to find this table or how to find this table? Variation of thermocouples reading T as a function of time. You will see in the Lab5 program, this is the temperature of thermocouples and Y, and the function of the time. So first, when we run the experimental at the temperature at room temperature, which is almost a 20, sometime depend on the room temperature, a 20 or maybe 20, 22, we don't know. So it depends on the room temperature. The temperature increase gradually with the time until reach the steady state. So to reach the steady state, it take sometime I don't that's sometime it takes 25 minutes to 30 minutes to reach the steady state. How do you know that you reach the steady state? When the temperature is not going to change with the time. It's not big different, plus minus 0.1. When we see that, it means we are reach the steady state. So when you reach the steady state, you need to find a temperature. You have in text file. I will send you the text file. You have the temperature with the time, and you have T1 and T2 and T3 and so on. You need to find the value, the final value from the text file that I will send it to you. The final value of T1, T3 to T8. These value you will use it to calculate the thermal conductivity and also with the by finding the T hot and T cold. So the relationship between temperature with the distance, and I need you to plot a temperature with the distance. So here the distance at y equals 0, T equal here, if I say this is Y and this is a T. Okay, to make a table. So the table, you can say at Y equals 0, T equal T1. At Y equal 15 millimeter, as I told you, then between two temperatures, distance between T1 and T2 equal 15 millimeter. Okay, this is T2. And then at 3, because we plus 15 millimeter, which is 30, which is T3, and this is 45, T4, this is 60, T5, 75, T6, right? 90, which is T7, and then 05, T8, right? This temperature. Once you have the table, you can draw a table. This is the distance. You see, this is 105, right? A distance between a temperature. You will find, you will draw, and then you can see how the temperatures are linear. This is why we call that linear conduction from the hot surface, to the cold surface. The temperature gradually goes down. There is another way. If you say, okay, I am going to calculate the thermal conductivity, I don't need to calculate the thermal conductivity by calculating a T hot minus T cold divided by delta Y, which is 30 millimeter. You say, I don't need to calculate by this way. I need to calculate from linear conduction, which is fine. Delta T over delta X, and then this is the R. You can find this is X equal, you say A equal Q delta T over delta Y over delta T. This is area. So delta T over delta Y. This is delta T over delta, and this is Y, right? So you can say, okay, this is K here, this is here, K equal a Q A, which is 1 over delta T over delta Y, right? You can apply this number 0.20474, and then you find the thermal conductivity. This is what I need you to calculate the thermal conductivity. There is another way to calculate the thermal conductivity by using the C-therm. This is very fast, very straightforward. You don't need to worry about the T-hot, T-surface, thermocouples. Just you need the C-therm with a TCI, which is in LabVIEW inside. And this is the cross-sectional area from this device that we added this, the sample, which is called MTPS. C-therm is an additional laboratory apparatus available for thermal conductivity measure. It is deemed faster, but perhaps less accurate. We don't know. Less you need to find. When you calculate the thermal conductivity, you need to write why you got this result. Compare this result with the result that you got it from the Google. So this the concept of application of the C-therm unit is one of the thermal infusivity, and in the program, lab program, you will find a table. I will send you a table. This table directly give you the value, the infusivity, give you the infusivity with the thermal conductivity of materials and the temperature delta T and resistance and so on. These value will give you a five different value of thermal conductivity for the material of BLA that we are going to calculate it. And then how it works. So first, and now current is applied to the sensor. There is a current what? Current apply to the sensor spiral heating element. This is the sensor, and then we added, this is the material that we are going to measure. We need to find the thermal conductivity of this material. So we added up. I will show you. Provide a small amount, so provide a small amount of heat contact to the surface, and then this surface is called the girth ring surrounding the primary sensor coil to support a one-dimensional heat transfer into the sample. The apply this is the sample. Apply current result in a raise in temperature at the interface between the sensor and the sample, which is induce a change in the voltage drop of the sensor element. After that, when we touch this surface with the sensor, you will apply to the Lab5 program. You will give you a direct information for the thermal conductivity, which is direct to gate. It's take maybe for each thermocouple, it take 50 seconds. So finally, once you find the thermal conductivity of metal, which is a brass, and find thermal conductivity of PLA, find the thermal conductivity of brass. You find it, thermal conductivity of PLA. You find it, you need to find the error. Experimental, you got it, this is from experimental. A theoretical, you find it from Google. And then you find it from Google. You find the error and then give the reason why you have this error. You see the big error, small error. By calculating these thermocouples, you find the error. Finally, thank you so much for listening to this presentation. This is just give you introduction. I will go to explain the experimental. Please feel free to contact me by either telephone number or email at any time. I'm willing to help you to understand the phenomena of thermal conductivity. Thanks.